Yeah, so hopefully it'll get done, but if not, you can like get the last bit of data from your
Okay.
partner or whatever.
Okay, cool.
I forgot.
I wasn't planning on it, but we can talk about it.
Sam doesn't like it. I feel like the floor should be, but it could just be in my head. Maybe when I lay down, I feel dizzy. Like my eyeballs, when I close them, they're like, so it could just be. But I remember that these too got Dr. Pepper that are Did they say that the doubters one was a mistake meant the doubters?
Oh, I don't know. I asked Nicole to tell me, so I haven't followed up. Hopefully,
Oh my goodness. Thank you, everybody.
maybe you're gonna see her.
Out of all the ones. Imagine that. Can I ask you a question about the homework, the chapter 8 homework?
Yeah.
So BR02, which is an ion that I probably know the name of. So it's a bromine and 2 oxygens, and the 2 oxygens are double bonded. Is it double bonded because it's the very last one on the second page? Is that double bonded to both oxygens just because of the formal charges?
So you put a double bond between both of the oxygens?
Yeah.
So let's check that out.
Wait. I think that's what I wanted to do, and maybe Dorothy had something different.
So let's look at the possibilities. So let's first do our total electrons. So how many electrons are in this system? Oh. So we get 20, right? And let's just start with no double bonds, and then we'll see. And so we put bromine in the center. Let's just start attaching. And so we have 20 electrons, so 1, 2, 3, 4. So what happens if we do this? So now we're at 8, 16, 17, 18, 19, 20. And then, so then we said, well, let's look at the formal charges. And so what's the formal charge on this oxygen? So -1. What's the formal charge on this oxygen? And then what's the formal charge on our bromine? So +1. And so this is like, I would say it's an okay-ish structure in the sense that we have the correct number of electrons. So that's always the first thing that I'm looking for in your structures, is do you have the correct number of electrons? But then you notice, well, we have 2 formal charges next to each other. So that's not quite ideal, so we want to minimize those formal charges. And so probably the best thing to do would be make at least 1 double bond. So let's try 1 double bond. And so I just move those 2 electrons over into a bond. And so now, no formal charge on the oxygen or the bromine, but then we still have a negative charge on the oxygen, so that's fine, since this is overall negatively charged, so it has to be somewhere. And then, let's see, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so it is hypervalent. And then, so could we make another double bond? Would that help? Let's just compare the structures. So what happens if we do this? And so now where's my negative charge? So it has a -1 formal charge. So this probably wouldn't be bad either, except so you probably want the negative charge on the oxygen. So I think the oxygen, oh, I didn't have a periodic table. There's not one in this room. So oxygen is probably more electronegative just because it's closer to fluorine. So ideally for like our best Lewis dot structure, we want the negative charge on the oxygen. Oh my gosh. One more try. And so again, I probably wouldn't mark you wrong if you wrote this structure again, as long as you put the formal charge, you have 20 electrons, but this is probably the best one since we have our negative charge on oxygen, which is our most electronegative element. So does that kind of clear that up?
I feel like I asked the same question, just in different like forms of the same question, but yes.
No, it's good because I want to emphasize, right, like, you know, we're always so focused on the right answer, but it's really about, can you analyze your structure, can you put the formal charges, and then you can kind of look at all these three possibilities and kind of say, well, this is probably the best that best describes the scenario. And then what you could do, you know, you have access to WebMO, so you can use it, and then so you could plug it in and then see what it spits out and see, well, which, you know, once we do the computational chemistry, which one matches our back of the envelope calculation the best. And that's kind of more of what we're going into with Chapter 9, is doing these back of the envelope MO calculations. What do we think the bond order is going to be? Where is it going to actually be able to bond? What orbitals are being used in bonding? And then we ask the computer and kind of compare. Other questions before we get started? I know you mentioned you had a bond angle question. Did you have a specific like example? Sorry, I caught you mid-bite.
I just don't understand the bond angles, like how to tell what they are, and like how to count bond angles. I don't understand it at all.
So let's just think of PCl5 for a second. And so, and y'all can tell me what you got in lab too. So PCl5, what's the expected geometry of this? Yep, so trigonal bipyramidal, or however you want to pronounce that. And so we know it's going to make kind of this geometry, roughly. And so hopefully what you found in your WebNote calculations, and so first of all, you had to click in the right order, which I think most people got eventually. But the angles we care about are either this, like what we assume to be a 90-degree angle here of chlorine, phosphorus, chlorine. So you want to understand that. And so that's where you can look back at your Vesper sheet. So we go back, it says trigonal bipyramidal, and then it tells you kind of, right, the idealized angles, so 90 degree here to here, and then 120 all the way around. So going back, so this is 90 degrees, again ideally 90 degrees. And then I don't know if you found little distortions when you actually ran it. And then this should be, so chlorine to phosphorus to chlorine. And we could redraw this, you know, top-down view. So that's a little more clear, right, that that's evenly, again, 120 degrees around.
So there would be 3 120s and like what?
And I would say 2 90s, since, I mean, this is about the same, but I guess technically 4, because you have 1, 2, 3, 4, but of course if one is 90 degrees, then they all were, but you saw, you know, sometimes you had like 89.9 from a small distortion, and that would make the other one like 90.1, and so forth. And then the other thing to kind of note is if we have, you know, the comparative, so now if we look at SF4, so I picked this one because it's in the same electron geometry family. So what's the electron geometry? So electron geometry and molecular geometry. So what's the electron geometry of SF4? What parent group is it in? So what's the hybridization you said? So SP3, we're missing something. D, yeah, so that's 5, right? And so we can draw out what it looks like. So hybridization, SP3D, since it's got 5 things attached to it, same thing as the trigonal bipyramidal. So then what's the electron geometry? So that would be the molecular geometry, right? So that's where your atoms are. So that's seesaw. Yeah, and so why I'm emphasizing the electron geometry is that we have to start with this as kind of the idealized thing. And then there is going to be some distortion. So I don't know exactly what WebMO gave you. If you have your answer handy, you can tell me. But I'm assuming that it's not perfectly 180 because you have more electron repulsions. Remember, lone pairs want to occupy more space. So if we had swapped this, you know, for a fluorine, that would obviously give you the even 120 or 180 across here, or 90. And so I assume there's some distortion. Oh, I guess the lab didn't calculate SF4. So in your free time, you could run this. But I would expect there to be some distortion. So I assume this is going to be a little less than 180. And so that will probably tighten up the little angles there. But that's all you're kind of looking for. And so again, ideally, here to here should be about 120. It's probably a little less than that. And let's see if your chart gives you any indication. And so, right, it doesn't give you an exact value. It just says less than 120. And again, we expect that it's kind of a little closer from the lone pairs. And so if we wanted to, we could run this on WebMO, get the exact angles. But again, we expect them to be a little smaller. And so it has less than 90. So again, I assume it's a little smaller from that lone pair distortion. Does that kind of clear things up? Other questions on angles and distortions? Because that's all. Yeah, so I would just go back to this sheet too because you're always starting with the kind of idealized geometry, and then as you add, more lone pairs, they start occupying more space and can potentially create distortion. Other questions before we start diving into chapter 9 more? All right, so let's look at chapter 9. And so with this chapter, ask questions, ask questions, ask questions. Because I've seen these pictures a bajillion times, but like if you're not seeing the translation, like, we need to slow down so that you understand what the heck all these pictures are showing. Let's shut the door. I'm gonna grab the back door. Thanks. And so your book kind of starts off with what I think is a not helpful picture, but let's look at it and look at what the heck they're trying to show us. And so first of all, what orbitals does H2 have? Like, what do we think about when we are talking about H2? So s orbitals. So hydrogens, right, they just have the s orbital. So 1s, that's all we're really focused on. And for some reason, your textbook just shows like all the other orbitals that aren't occupied. And I find this a little frustrating because I don't think it's very friendly. And so all this is, yeah, let's actually go back to this, because I think if we start here, it'll be complicated. And so let's just look at our basic, let's just start with H2 plus. And again, all we really care about is the 1s orbital. And so to make our MO diagrams, you want to start with whatever atomic orbitals you have. And so we have two hydrogens coming together. They're each bringing with it an s orbital, or 1s. And so I like drawing the little pictures. And then so we have to make our two possible combinations. And so we have our mathematically favorable combination where they're what's called in phase. And formally all that means is they're the same shading. And so by convention, I'm just going unshaded. You could shade them both. It doesn't matter as long as they are the same. And so we have our first kind of bonding orbital. And so this would be our 1 sigma orbital, so our bonding. And so if we have our bonding combination, mathematically we also have to have the opposite, our anti-bonding combination, where they are not in phase. And so that's going to be opposite shading. So now we put 1s. The little star means anti-bonding, so that's not favorable. And so now what we would do, I probably should have drawn this better. So this is my MO orbitals in the middle, so our molecular orbitals. This is our combined. And now we can tell our bond order too. So this is H2 plus. So how many electrons are in this system? So 1. And so we would just fill in one little electron there. And so notice I draw it as just an up arrow. And so I'm just doing it in the up spin. You could do it opposite, and that's all it is. And so now we can calculate our bond order. And so our bond order is we're just going to have the number of electrons in bonding orbitals minus the number of electrons in anti-bonding, since again that's not favorable, and divided by 2. It should all be in parentheses. So what's our bond order for H2 plus? we only have 1, but then we have to divide it by 2. So 1/2, or 0.5. So our bond order for H2 plus is just a half now. And so that would just kind of mean, right, they have like this half bond. And so the species probably isn't very favorable. And so here's our chart up here. And so all this is saying is the same information. So we have 1 electron. And then by this ground state configuration, all this is saying is we have 1 electron in that sigma 1s orbital. And again, sigma meaning that direct bonding. So they're next to each other. So that's sigma.
So why is there no electrons in the
Oh, just because we ran out, essentially. So right, this system, normally each hydrogen contributes 1 electron, but it's a plus sign, so we just have 1. And then you just fill in from the bottom. So it's just favorable. You start from the bottom. That's all we have. We ran out. Yeah.
What's the formula again for the bond order?
So you just take the number of electrons in your bonding. So we had 1 electron in a bonding orbital minus electrons in anti-bonding. So we didn't have any in the anti-bonding. So minus 0, and then divided by 2. So you always divide it by 2 at the end there. And so here they actually have, you know, what the bond length is. So if we had spat this into WebMO, it would give us a potential bond length, which should be somewhere around this. So now let's look at H2 for comparison. And so H2, I'm more familiar with. So again, just start H and H. So 1s, 1s. I'll draw it a little better this time. So again, our in-phase combination. Then we have to have our out-of-phase combination mathematically. And you can also draw in your electrons on the side here. And so they each bring 1 to the table. So then you start from your lowest orbital. And so we'll just fill them in. And so the 2 go in the lowest orbital. We ran out, so none in the anti-bonding. And so what would the bond order be for H2? What do people say? 1. So it would just be 1, right? So we had 2 electrons in our bonding. And we should label this as sigma. This is 1s anti-bonding. So 2 minus 0 divided by 2 gave us 1. And then we can always compare this, right, to our Lewis dot structure. And so we not too much to examine here. So this is what we would draw, right, for our Lewis dot structure. There's 1 bond. It matches with our bond order. And so that all looks nice there. So that matches here. And so now let's look at this helium-2 plus and see what that looks like. Question? So anti-bonding is just like the unfavorable, it's like a mathematical thing. Because if you're combining them in phase, it also has the possibility of being out of phase. And it's just when they're out of phase, they can't bond. So it's like, that's why. And we'll look at a WebMO picture. Because what you'll see is kind of like this orbital. Actually, let's look at that now. And so what you can do, if you're bored, is so you can plug into WebMO and I'll show you later. But basically, sorry, I don't want to screw up my jobs. let's look at it. I'll show you what I did. So we can look at, hydrogen. And so what I would first do is do a molecular energy, so that just optimizes the energy. And you can change that around depending on how long you want it to take. This should be fast, hopefully. There we go. And so once you've optimized it for energy, then you can just do a new job with this geometry. And then instead of doing a molecular energy calculation, they have molecular orbitals. So you can click that. Let it run for a second. And so now we can look at the pretty picture that they give us. And so here we are. So it makes this nice circle. And so this circle is just your bonding combination. And so that's just another way to write it. I just leave it like this because, again, we know I have no artistic skills. But really, right, it's making a bond. So it's going to create that bonding orbital that looks like that. And then if we check out the antibonding orbital, so here's our antibonding orbital, and so you notice, right, there's a node here that separates them so they're not bonding. And so that's also what we mean when we say bonding and antibonding. And then for some reason it just gives you higher orbitals, and again we'll look at that, what that is. So this is the PZ, and you can tell it's unoccupied, so it has 0 electrons here. That's why I don't even bother talking about it when we're looking at H2, but we'll go back to what the book spat out, because the book was just showing, again, all your theoretical orbitals, but we don't want to start there if we can't understand, the 1s first. But that's all that these two higher ones are, and so this would be your P antibonding orbital, and so you can tell, right, it kind of has that dumbbell shape to it. Obviously it gets a little refined, and then they're out of phase, so right, the green shading doesn't match the yellow, so you know they're not bonding. So this would be your PZ antibonding. Let's see, where were we? Oh yeah, we were at helium. And so we said, let's look at the helium diatomic plus. And so again, right, it's still in the first row. We only have our 1s really available. And so we'll put one helium and another helium. Fine. And so, right, each one normally brings 2 to the table, but we have a plus charge, so I'll just put 2 here, 1 on the other side. And I'll draw my circles. And so again, now we'll put our in-phase combination, so our 1s bonding. And let's draw our anti-bonding phase. And so the other thing to keep note of, so it's easy to see now, so if you start with 2 atomic orbitals, you should have 2 molecular orbitals in the middle. And so that's always good, and that's more helpful when you're combining, obviously, more orbitals. And so now we can fill them up with our electrons. So again, we have 3 electrons in this system. So we just start at the bottom, so 1, 2, 3. Now we can calculate our bond order. And it's now our bond order. So we have 2 in a bonding orbital. And so this is our 1s antibonding, minus 1. divided by 2. So what does that give us for our bond order? So 1/2. So again, probably really weak interaction. I assume this only exists in the gas phase anyways. And just double checking, yeah. And again, that's what we're showing here. So notice 2 occupied in our sigma 1s bonding, 1 electron occupied in our sigma 1s antibonding. And so now we can answer why helium is not a diatomic, so why the noble gases are not diatomics. And so let's look at that. So helium, so our 1s, so helium, so each bring 2 to the table. So 1s bonding, 1s antibonding. And so now when we fill in the electrons, so we have 4 total. So 1, 2, 3, 4. And so what happens when you do your bond order calculation? What's your bond order? So 0, so no bond. So we have 2 in the bonding minus 2 in the antibonding. Oops, forgot my antibonding there. And so that's why, again, helium-2 doesn't exist. All right, so we're good on the 1s so far, or at least just looking at helium and hydrogen bonding. Yeah.
So the 2 circles at the bottom of your figure, and then the 2 circles at the top, can you explain what those are again?
So they would just match. So this is our bonding. So if they're bonding, then like ideally mathematically you want to think about them making like one big circle. So again, looking at this H2, right, the big circle. So this is a 1s bonding then.
So on
Words.
your drawing, is one of the anti-bonding circles shaded in because it doesn't exist? No, like on yours. So the anti-bonding, that one. So is that shaded in because there is no electron there?
No.
Why is that shaded?
It's just shaded to show that they're out of phase. So it's a mathematical thing. Because basically what you're answering is how many ways can you mathematically combine this and this? And so it doesn't matter, right? They could be shaded, and that would still give you. So basically this plus this gives you a giant blob. This is the same thing because it's still a giant blob. So it doesn't matter. But then when you have the out of phase, and so that means that they can't combine. And so that's where you get that node there. And then again, it doesn't matter if you had done the other shading, right? It still gives you mathematically the same thing. So that's why we just have this one and this one, right? These are just redundant, essentially. All right, so let's see if we can look at the next orbitals. And so now let's actually look at, what do I want to look at? Let's just look at generic A2 for a second, because I don't want to get into the next topic. And so now A2, we're going to invoke p orbitals. So this is probably, let's just say it's second row. And so that means that we're mainly focusing on, right, the valence orbitals. So that's going to be 2s and 2p for this one. And so the other thing is, right, well, what happened to the 1s? And we'll look at a calculation on WebMO, so you can, kind of believe me. But basically the 1s, so those are core electrons, so they're not involved in bonding. So we don't care about them necessarily. And so we'll also kind of look at this picture for reference and correlate them. And so now let's just start, again, generic A2. I just want to build kind of our framework. And so now we have our p orbitals. And so they're degenerate, so just remember that. So they're all the same in energy. I just draw them close together. And we haven't defined any of them yet as separately, right? Px, py, pz. We'll get there. And we have our s, so I'll label this as 2s and 2p. 2s. And so let's just start with our s orbital and our pretty pictures. So our s orbitals, so they're still circles. And so we'll just start just like we did before. So mathematically, we said we have our in-phase combination and our out-of-phase combination. And so now we have to think, well, what are the p's going to do? And so we're thinking about generic AA. This is probably going to be the z-axis, again, just for formality, since that's the axis of highest symmetry and rotation. And so what orbitals might be prime to bond? And what kind of bond will they make? So we could do a pi bond, and so this is a z-axis. Which ones would be pi bonding then? Yeah, so px and py. So pz, and we'll go back to pz. But now we can start thinking about our px and py, so I'm just going to draw them first over here. And this is just because I like to see what we have. So I'll just put px up and down. You could call that py. It doesn't matter. And then so py is coming in and out of the plane of the board. And so now we have, right, our two possible combinations. So we have, let me scoot this down a hair. And so, of course, we have, right, our bonding combination. And so now these are going to be degenerate, right, because px and py, we can't tell the difference. They're just in different axes, so they're the same energy. So they would go here of our two degenerate orbitals, so they're really close to show that they're close to each other. And so now this is our pi bonding. And then you can draw them. So we have px where they're in phase, and then py where they're in phase. And again, all the in phase means is these two are the same color now. So your p orbitals, right, they have opposite shading on the orbitals, but then you're just looking for that through space interaction. So, right, you have that pi bond through space. So through space. So these two have the same shading. And so, of course, if we have a favorable bonding interaction, mathematically, we have to do the opposite combination, right, where you're adding them now out of phase. So now your out of phase combination, that's your anti-bonding orbital. And so, again, that's unfavorable. That's going to be higher in energy. And so now this is our pi anti-bonding. And we can draw the pictures. So now the shading is opposite. So px and then py. Okay. And then which one are we missing now? So we have PX, PY. What about PZ? What's that one doing? What'd you say? Sigma, exactly. So now there, and we can think about them. So we have, again, two possible combinations, either where the middle is in phase, so now they can bond, right? So that's a nice sigma interaction. And so this would now be lower than these. So how it goes is like by favorable overlap. So this is favorable, that's why it's at the bottom, it's the lowest in energy. And then we know to put this PZ interaction lower than this one because it's more favorable, more direct. And again, it's because it's at sigma. Oops. And it doesn't matter if you shade the inside or the outside, just as long as they're in the same phase. And so now this is our 2 sigma bonding. And so of course, if we have a bonding scenario, we have to have an anti-bonding scenario. And so this anti-bonding orbital, where the middles don't match, is actually higher in energy now, since now that's really unfavorable. So this one, yes, it's unfavorable, right? But it's a pi bond, so it's through space. But now that sigma one's really unfavorable, so that's high in energy. So now that's up here. And again, doesn't matter which way you shade it, just as long as these don't match in the middle. And so, right, this was our 1s antibonding, and so now this makes this 2 sigma antibonding. And then double check yourself. So we had 1, 2, 3, 4, 5, 6, 7, 8 atomic orbitals. So that means we have to have 8 in the middle. So 1, 2, 3, 4, 5, 6, 7, 8. Let me zoom out a little. So now we know, okay, everybody made it in there. All right, so this is your generic picture. And so I would label this as just kind of generic picture and add under here no SP mixing. So we'll answer what the heck is that in just a second. But now let's look back at our hydrogen and see what the heck they were trying to show us. And all this is the same thing we just finished drawing. Right, so we have our s orbitals down here. So our 1s bonding, this would be our 1s antibonding. And then something, see, I'm trying to even figure out what they did. Yeah, and then they did 2s for some reason. So now this is 2s bonding, 2s antibonding. So they're, again, just showing a bunch of orbitals that aren't normally invoked for hydrogen. Now this is our P X and Y interactions, and so they drew them as degenerate, so they're the same line here, so we normally draw them like that. That was all this was. So that would look like that pictorially. They just drew the sigma bond. So this is PX, right? That's PY, which they didn't really show that well. PZ, so they just have that there. And so notice the way it's drawn here. So you have, this is our pictorial representation, and then they just kind of redraw it to show like, okay, these two would combine to make that center one. And then of course this is out of phase since the p orbitals, right, normally have that node. And so that's how you get that picture. And then these are just the anti-bonding pi orbitals now. So that's all that's showing. So px, py, and then this last one is that unfavorable anti-bonding pz there. So does this picture at least make sense now of what the heck they're trying to show? Again, I'm not quite sure why they did this, but I don't think it's the clearest way to start, but that's the translation. All right, so now let's try to understand SP mixing. So we're going to kind of redraw this diagram. But before we dive into it, so what do you notice? What do you notice about like what orbitals go in the same direction here? And where might there be SP mixing, I guess is what I'm trying to ask.
The X, PX, and S.
So maybe not PX, but because try to stick with this convention. So I like the S though. So what would mix there?
The PZ.
Yeah,
Sorry.
exactly. So we're going by this convention, and that's again why I at least try to keep Z the highest order of symmetry. We're seeing, well, these are basically the same, so maybe they could SP mix, and then that would make this one lower in energy, so that would be really favorable. We would eventually pay the price on this one, but again, we always start filling the electrons from the lowest one first, so if we can SP mix, that would be favorable. And so now let's kind of look at, well, what is SP mixing? And so basically, and so here's where there's a switch. So lithium to nitrogen, all these simple diatomics, these do SP mix. And so the other reason why we can invoke SP mixing is that there isn't a large gap between the P and the S orbitals. But as we get further down and more electronegative, now there's no longer SP mixing. So now the S and the P are just too far apart now, and so they don't really mix. And of course, there's always some sort of element of mixing or not mixing, and you can kind of see that from this chart. So of course, neon, right? Again, you're just kind of appreciating how far apart they are. So our 2s is really down there in energy comparatively, and compared to, right, the lithium, where it's a little closer to that p orbital. So here we can mix. And so what changes then is our order. And so looking back to what we drew here, this is our unmixed order. So notice it goes right sigma, sigma antibonding, and then we go just that single one next. So right here is no mixing, so same order, right? Single, single, then that single sigma. But once we do mixing, we this drops lower in energy, but now that means we kind of have this, I call it almost non-bonding orbital. So now we'll go through it though. You can see how they swap places. So now your degenerate ones are actually lower in energy than your kind of middle SP mixed one. All right, so now let's go over it kind of in more detail. And so now we're going to redraw kind of generic A2, but now with SP mixing. So A, and let's just start. So our 2P, X, BY, PZ. Of course, our 2S. Again, we're not looking at the 1S since it's, again, a core. And so now I'll draw kind of my Z orbitals. And so now we have to think of the most favorable bonding combination. And so, of course, the most favorable for sp mixing is going to be when they're all in phase, right? So that means our two s orbitals are in phase, and then also our pz is in phase. And so that would give us, right, a really favorable bonding interaction. So now we kind of emphasize the lobes in the middle. These little guys kind of get downplayed. Again, you're just kind of thinking, if I could pictorially take these two unshaded circles, place them on top of these two unshaded circles, right, it would make a bigger unshaded circle. And so this would, again, be comparatively lower in energy compared to our non-mixed one, because now you're thinking, right, we had just two regular s orbitals mixing, but now we have that bigger size, so more favorable overlap, so that's lower in energy. So that's our lowest one here. So our 1 sigma orbital. And again, we'll draw it something like this. And so now we'll get back to the middle in a second, because it's easier to figure out kind of your best combination, your worst combination, and then you can figure out what's in the center. So now what I kind of call, right, the worst is where they're both going to be out of phase. So of course, right, where these two are out of phase, mixing, where they're in phase with the p orbitals, in the sense that right now we're emphasizing the worst parts of it. So this unshaded matches with an unshaded to make this big and unshaded. And then our center gets big and shaded. And so now that's a really unfavorable interaction. So this is the price we paid for that one. So that's going to be our highest orbital. So again, we had to pay an energy price. That's just what mathematically had to happen too. So now this is really unfavorable. It would be higher in energy compared to just this regular one, right? So again, you're just kind of thinking pictorially, overlapping. You know, yes, this is not great, but now this is really not great because we have larger lobes in the center there from mixing. So then we have kind of our two other combinations where this is going to be in phase, but then it's going to match with our z orbital, which can be in phase with each other, but out of phase with this. And so what that does, right, you can kind of imagine these circles canceling out. And so that gives you a larger lobe on the outside and then a smaller lobe on the inside. And so this will be, right, it's formally bonding. Oops, I didn't mean to put an anti-bonding star on it. So it's a formally bonding orbital, but really what it's showing here is there's not a lot of electron density in the center. Most of the electron density would be in the outer lobes there. And you could almost write, you know, non-bonding on there. And then we have our other combination, and so we'll put where these go in a second. And so our other possible combination is where they're out of phase, but then the p orbitals, so the p orbitals are also out of phase, but they're all out of phase with these circles to kind of minimize that interaction. So then this again minimizes the center, so it becomes almost essentially non-bonding, and our electron density would be on the outside there. something like that. Again, formally anti-bonding, but essentially non-bonding. And so this one would go next in energy. So this is what would go here. Or kind of non-bonding-ish one. So now that's our 1 sigma anti-bonding. And then, so the next thing to figure out is, well, which one goes next in energy level? So if we look back to this one, right, we had the Z axis next, since that was nice and overlapping next to each other. But once we mix, right, so we use this one, so now we're kind of debating between this non-bonding interaction, or is the p orbital higher or lower in energy? And so what we find is this has more favorable overlap, since this is, again, essentially non-bonding. And so that's why those are next in line here. So now we put our degenerate p orbitals. So now our pi bonding. And again, that's our through space interaction, just like before. So this hasn't changed, right? It didn't sp mix. It's not in that plane, so we didn't touch the px or py compared to our previous drawing. And so now we can draw them. So again, that's our favorable interaction. And I'm going to go ahead and write the anti-bonding orbitals before I forget. Since again, I always just like to write your bonding and anti-bonding at the same time. You always have to pay that price. Oops. Sometimes my pen doesn't like shading. And so our last one we have to squeeze in somewhere is, well, where did this guy go? And so now it goes kind of in the center here, just above this pi orbital. And again, almost non-bonding, formally bonding though. And so there's our, now it would be, so we're at 2s here. So our 2 sigma, almost non-bonding, formally bonding interaction. And again, it's not as favorable, that overlap, since we have small nodes in the center. Oh, and then just double check yourself for sanity. So 1, 2, 3, 4, 5, 6, 7, 8. So, okay, all 8 made it in the center here. So now let's look at, well, here's a couple of things. So now we have our cheat sheet, as we can call it. So, right, we have our generic picture. So anytime we see oxygen, fluorine, or neon, all we have to do is refer back to this and then fill in your electrons appropriately, because the only thing that distinguishes oxygen, fluorine, and neon is, of course, the amount of electrons. And they've filled it in all for you here, but we'll go through this ourselves. We can't just trust these pictures. And then anytime you see, lithium to nitrogen, you can just plug it into this generic picture, right, with this ordering of electrons. And again, the only difference is the number of electrons here. And so now let's look at nitrogen. So we can compare our drawing to their drawing, and then we'll look at it on WebMO and see how that would look. I'm just going to start a new page. Oh my gosh, now I started too many pages. Oh no, sorry. Sugar happy. And so nitrogen, starting again with our diatomics. And so we know that there is sp mixing. And to me personally, I would draw out the little pictures still, just so you know what the heck is going where. And then we could fill in our electrons so we know what we're starting with. right? And that just matches with our electron configuration for nitrogen. And we're only looking at the valence electrons right now. At least that's all I'm putting in here. So how many electrons are there total? So 10, I'll just write that at the top, so 10 electrons. And so, you know, if you need to look at that and refer to it, I would, but that's all we're just gonna be kind of recopying. And so I'm just gonna redraw it. So again, our most favorable combination, where they're in phase. Then we have to have our out of phase combination, but again, we minimized that out of phase combination with the SP mixing. Sorry, OneNote doesn't like these little circle shadings. So now our 1 sigma antibonding. Then next in line, we said were our p orbitals. So those pi bonds, so px, py. Next was that almost non-bonding. Let me redraw that. Where we had minimized electron density in the center, formally in phase with each other. So 2 sigma bonding. And then our next one, so now we have to write our pi antibonding. Again, degenerate. And then finally our last one, oops, I started off, our really bad out of phase combination. Then as always, double check your sanity, like 1, 2, 3, 4, 5, 6, 7, 8, okay. So now we can fill in our electrons. And again, we're just looking at the valence electrons in this graph. And I'm emphasizing this because WebMO is going to show everything. And so now we start from our bottom. So putting in, right, 2 electrons in each orbital. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 here. And so let's just compare that. So now we can introduce other terms. So we have what's called the HOMO and the LUMO. So HOMO stands for highest occupied, I can't spell today, occupied molecular orbital. So our HOMO in this case is going to be this 2 sigma, and right, that's just the highest orbital in energy that's occupied. And so LUMO is lowest unoccupied molecular orbital. So then this would be our LUMO, so it is degenerate, right, our degenerate p orbitals. And then, of course, let's just compare to the textbook drawing. And so, yes, they got the same thing, right? So, again, our HOMO being that sigma one, so we could tell that it's a 2s since it's just by itself, not degenerate. And then we can tell, right, that's the LUMO, our degenerate p antibonding. Oh, and then let's go ahead and calculate the bond order then for nitrogen. And so bond order, that's where we take, again, everything that's formally bonding. And so just watch out, because we have that anti-bonding one. So we have 1, 2, 3, 4, 5, 6, 7, 8, right, in bonding orbitals, minus these 2 in the anti-bonding. So that's 6 divided by 2. That gives us a bond order of 3. How does that compare to our Lewis dot structure? So how many bonds do we expect in our Lewis dot structure, or what do we get? So 3, and so that matches nicely. So this would be, right, our Lewis dot structure for nitrogen. Bond order matches, so that's cool. It kind of, you know, again, tells us what's going on. We can look at what orbitals are actually bonding. So we can see all that. And then we can also see, right, probably these electrons are going to be in this orbital, in the 2 sigma here, where we have, again, high electron density. And so now let's compare that to what WebMO would spit out. And let's see if it saved my job. Where is it? So here's N2 over here. And so notice the first thing. So it gives you your 1s bonding and formally anti-bonding, even though those are core electrons, so we don't really care about them. You can kind of tell they're core since they're really low in value. And so it's just spitting out, right, its energy that it's calculating. And so lower is more favorable. So it has these as -15. So again, we don't really care about them, but they're there. And so you can see that these are going to be centered on the atom. So again, they're not participating in bonding. We can see that. And this is just mathematically the formal out-of-phase combination. Again, it's centered on the nitrogen, not involved in bonding. So again, we don't write that on our MO diagram. But now we can compare, so what's next in energy level, and kind of see, does it match with what we calculated? So now this is, right, our 1s, or excuse me, our 1 sigma here, right, our bonding combination. So just a nice blob. And then it tells you the occupancy. And so notice why I was emphasizing we're looking at all of them versus our core. So let's see, nitrogen would have, what, 12 total if we included the core, or 14? I can't do math. Yeah, 14. So 1, 2, 3, 4, 5, 6, 7. So it's including all the electrons in there, right, including the core. So we were only looking at these 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So our MO diagram starts again right here. And then we go up. So again, that's our formally, our anti-bonding orbital that looks like that. Then we have our next orbital. And so sometimes, so it looks like it put the PZ next or something, which is not what we would expect. So the ordering could be a little off. It depends too, like what base set you use and all that. So that could, or maybe there's not as much mixing as we think. And so there's your PZ. And then you can tell these are 2 degenerate P bonding. Oops. And so now these go into the anti-bonding orbitals. So again, you can tell they're degenerate, they're the same energy level. Now this is your PZ anti-bonding. And now it's just going into like higher order orbitals. Let's see, so we only care about, so 1, 2, 3, 4, 5, 6, 7, 8. So I think this is the last one that we drew. So this was the most unfavorable interaction. And then the rest are just, so you can see it just kind of goes on and on with like the rest theoretical orbitals that are unoccupied. Questions about that so far? So let's see. So take a second. So draw out lithium for yourselves. So Li2 here. And then we'll compare that to neon. So lithium, we'll look at neon as well. So take a few minutes, get used to drawing these. And so as you do these, make sure you predict a bond order, and then kind of think, what would your Lewis dot structure say? And then, so don't forget, as you do neon, right, neon has no SP mixing. And so lithium does, right, so you should be copying or, you know, kind of using this one as a guide with our SP mixing. And so that's the order I put it in. So again, our most favorable one at the bottom, our kind of formally anti-bonding sigma on top. Then that leaves us next with our pi interactions as more overlap, more favorable, so lower. Then next, that kind of non-bonding one in the center. And of course, you can continue. But what's our bond order then for lithium? So 1, so we have 2, right, in our bonding orbitals, so 2 minus 0 divided by 2. So that gives us a bond order of 1. And so we can also say that it's diatomic. And do you remember what the term diatomic means? Or not diatomic, diamagnetic. Do we remember what diamagnetic means? So that just means that it has paired electrons. And so paired, they're in the same orbital there. So we don't have any unpaired. So if you have an unpaired, that would be paramagnetic. So you have some sort of unpaired electron. And I almost forgot we end class at 12:50. I was getting way too excited about this. This is like my most favorite topic in chemistry. And so neon, when you draw this one, so now we can't invoke SP mixing. It should feel a little easier to do. Maybe that's just me. But now we don't have to worry about mixing. And so now we can follow this generic A2 without mixing order. So again, the only difference is these orbitals swap. So now this one is going to have, again, the PZ back to being the lower one with that direct interaction. So our sigma from our PZ. And then that leaves us with our pi bonding orbitals next, our degenerate ones. And so now fill in the anti-bonding. And so how many electrons are in this neon system? When you draw them in? Or what's kind of the problem? So what do you get if you try to draw like a Lewis dot structure diagram? So we have neon, right? We could put in all 8 electrons. That's kind of crazy. And trying to figure out, well, how the heck can they even go together, right? And or what do you get for the bond order? So how many electrons should I put in here? So 16. So start at the bottom. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I should have zoomed in. 11, 12, 13, 14, 15, 16. And so now if we subtract them, so right, this is our sigma antibonding, pi antibonding. So now if we do our little formula, so let's just take our number of electrons in bonding. So 1, 2, 3, 4, 5, 6, 7, 8 minus 1, 2, 3, 4, 5, 6, 7, 8. And well, there's a problem. There's why, you know, trying to make a Lewis dot structure doesn't really make much sense. So what's our bond order? 0. So 0. And so now this explains why neon 2 doesn't exist. So not be favorable. Yeah.
So why does neon have no SP mixing but lithium does?
So it goes back to this chart here. So it's just that the p orbitals and the s and neon become so far apart that it's just not favorable to interact. So as you go across, there's like different degrees of sp mixing. And so like this one would probably mix the best, and then as you go across, right, they're farther in energy. And so if you were doing like more precise calculations, you'd be able to see that like there's different degrees of sp mixing. And so, but the rule is, once you get from oxygen on, so oxygen, fluorine, and neon, you just assume no sp mixing. And so that's all that's showing. All right, so I guess we're out of time. So on Thursday, we'll look at oxygen, and hopefully I will be able to do a demo, and we'll look at this more in detail. All right, I will see half of you in lab in 30 minutes, I guess. Oh, and then I have quizzes to give back. And thank you for being online. Thanks for checking in. I will stop this stream.